Thank you, Johannes, so much for the introduction, and of course, thank you to the Effect team for inviting me to speak here today. I'm Ethan Niser. I'm currently a freshman at the University of Florida, and since I discovered Effect a few years ago, I've just been a really, really big advocate of it, and mainly through creating content, especially on YouTube. And last year, I was at Effectis 2024. This was me in the hotel, work on my workshop, and that was a great experience. And so it's really great to be back here speaking this time. That last year was in Austria. This year was in Italy. I think by the time I graduate college, I'll probably have been to every country in Europe, just going to Effect conferences. But you can find me everywhere online at Ethan Niser. So if you couldn't tell from the title, kind of gave it away, but I did rebuild Redis with Effect. It's called Effectis. I didn't implement everything, but there is quite a lot. It's fully compatible with the official Redis CLI and official Redis clients. And while we are going to be looking at some code today, I don't want to get into the nitty-gritty too much. And so I want to start by first discussing why even rebuild Redis in the first place, right? It's not like the official implementation really needs replacing. And then assuming we have a good reason to do this, I'm kind of looking at what Redis represents and its different components and what might be hard about kind of implementing those things. And then, of course, we're all here for Effect, so how can Effect help us take on those challenges? And then the last thing I wanted to look at was a kind of brief analysis of performance and kind of how that comes into play with Effect. So I think almost everyone has probably used Redis before. It's an in-memory key value store. But really, it's a lot more than that. And that was something I think, got to see a lot through this project, was just how deep the Redis iceberg goes. I didn't know about eval. You can send Redis a string of Lua code to interpret. That was pretty cool. I think what's really great about Redis as a project is that it represents a very diverse set of requirements. There's a lot of things going on in Redis. And I like to think that everyone has a pretty good idea of how they would implement Redis in their own kind of favorite framework or language of choice. And I think how you go about doing this reveals a lot about the framework or language that you're using. And so by showing you how I used Effect, I hope it reveals a lot about Effect itself. So of these kind of different components of Redis, I think there's kind of this correlation between, as you go deeper down the iceberg, obviously things get a bit more complex. So at the start, we just have a simple map from string to string. I think everyone can do this. And then we have networking. So we have a TCP server. That server needs to operate on some kind of protocol. Redis has complex data types, so not just strings. There's like sets and arrays. Then in Redis, keys can have an expiration. So now you have like something asynchronous. There's timing. You might need to do some garbage collection. Persistence, so this involves writing to the file system. PubSub introduces push-based updates, so not just request response. And then transactions, you need to provide isolation and atomicity. And then at the very end, we have clustering, which is obviously very hard. Effect has a whole library for this. So while I drew these out in kind of a linear path up here, you've probably seen this chart before. This is from the Effect landing page. And this is probably, I think, in a couple other talks. But really, these features just exponentially grow in complexity. But I really hope that I can show you that some of these higher level features, especially transactions and clustering, aren't so hard given the kind of strong foundation that Effect provides. So now let's look at some Effect. So to start with the networking, so Redis operates on a TCP model. So every connection gets its own TCP connection. And this is done in Effect using Effect Platform. So if you don't know what Effect Platform is, it's platform-independent interfaces with platform-specific implementations. And one of those platform-independent interfaces is the socket server interface. So we can use this in our main Effect, and then we give it a function to handle every new connection. And then through the power of dependency injection, we can give it different implementations. So the one in the actual Effectis code, we're using this top one here, node socket server.layer, and this creates a TCP version of a socket server using the node net package. But you could just as easily run this over WebSocket if the client supported that as well. This one, I think, uses the WebSockets package, but for example, you could also use uWebSockets as long as it conforms to the same interface. So this function, the handle connection function, takes in this socket type. And with the socket type, we can call this socket.toChannel function, and this converts the socket into a channel. But what is a channel? Well, one of the things that's really great about Effects is the kind of primitives it provides, and channel is one of those primitives. So channel is really the core of the stream types in Effect. So people might be more familiar with the streams in Node.js, and so you can kind of think of channel as the Effect equivalent to a node duplex stream. So this is a stream that can be both read from and written to. And the other two types of streams in Node, which are readable and writable, both have their kind of rough Effect equivalents in the stream and sync types. One of the things you might notice right away about these types is just how many type parameters they have. This is really what makes them so great. And it shows just how much information they're able to encode and really how much information that the node types are leaving out. In addition, the Node Stream APIs, they leave a lot to be desired. Those APIs are pretty old, almost older than me actually, and especially around type safety and also kind of ergonomics. The more modern web stream APIs, so transform stream, readable stream, and writable stream, they're a little bit better in type safety. They're kind of generic over the types they operate on, but they still have a lot of the same issues, especially around their kind of imperative callback-based API. In comparison, effect stream types bring along all the benefits of the normal effect type that we're used to. So they have, they're fully type safe over success, error, and requirements. But that's really just the beginning. Just like effect streams are lazy by default, they have seamless resource management and interruption, and of course they're fully declarative, so no messy callbacks or listening to like string events. And just like all the other modules in Effect, there's just tons and tons of utilities for all of the merging and piping and literally everything you could ever need. And so the way Effectis is set up is really as this like pipeline of a stream and different transformations on that stream. So we start with some like bytes in, which just come straight out of the socket. And then we need to parse that into a string and then parse that into REST, which stands for the Redis serialization protocol. And then with that REST, we can parse that into individual commands like get and set. And then we run that against our storage. Oh, I'm supposed to be clicking through here. And then we run those against our storage to get some REST out. And then we can convert that back into bytes. And then given these kind of functions, these functions like take in a stream and return a new stream with a different type, we can compose these all with flow to get a single function from a stream of bytes in to a stream of bytes out. You could also represent this as channels. So instead of like a function from stream A to stream B, you could have a channel that takes type A in and returns B out, and you can just kind of also pipe those channels through each other. I thought it was a little bit easier to think in just streams, but streams are actually implemented with channels under the hood, so it's kind of the same. Although if I were to do it again, I would probably use channels just because of some of the more niche things that came up later, but the Stream API is generally kind of more ergonomic, and so I would probably reach for that first before you move on to channels. So this bytes to REST and REST to bytes part is a pretty important part of the app. And we need to parse in raw strings that come in looking like this. So the first character says kind of what the type is. And so a star represents an array. It's an array with 2 items. And then there's a separator, which is a carriage return and a new line. And then we have 2 different items. We have like the plus indicates a string, and then the minus indicates an error. And so what we really want to do is parse this into a kind of in-memory representation that we can pattern match on, and that would kind of look like this. So we'd have an object with like a type array, and then it has an array of these objects which have their tag and then a value. And this actually represents a really great use case for effect schema, because effect schema can encode both like a 2-way transformation. So I'm going to show an example for this simple string type. And so this is the one with like the tag simple string, then the value OK, and we're converting from this like plus OK carriage return new line. And so the first thing we're going to do is declare the kind of final schema for the in-memory type. So we're using schema.tagStruct to create like the object with that string tag and then the value of type string. And then this schema represents the transformation. So it's kind of a lot, but if you kind of look for, like from the top down, first we're like, this is like the input type, so we're taking like a string, and then we're making sure that it starts with the prefix we expect, and we're making sure it starts with the suffix we expect. And then once we know that, we can kind of chop the ends off and then make a new value, a new instance of the struct with that inner value. And then on the encode side, we can pull the value out of the struct and then put back on the prefix and the suffix, and that's pretty much it. And so this is for that simple string. There's a couple other types in RESP, and we can do this for all of them. And then we can make a schema union of all of them. And we actually end up with a single schema that can encode and decode from any REST string to any REST object and back and forth. And that's pretty cool. So now that we have some kind of REST, we need an actual storage engine to run it against. And I implemented this as an effect service. And it has just one kind of function called run, which takes in a command. And this is a command like get or set, and returns some like output RESP. And so the theory, with this kind of service is that, while for Redis it's probably an in-memory store in theory because it's just like an opaque service, it could actually be writing to the file system or writing to an object store over the network. And so I created just this like in-memory store type that kind of looks like this, which just has this one like store property and then the function that operates on that store. And so that store type looks like this. So it's a hash map from a string to this stored value. And stored value is a tagged enum, and this is a type from the data module in Effect, which kind of makes it easy to create like a tag discriminated union. And so it maps like from the tag to the actual like in-memory representation of that type. So there's like a hash set or a hash type in Redis, and that maps to the like hash map type from Effect. And we're using a lot of Effect data types here. Something to point out is that all of these Effect data types are immutable, and that'll be important a bit later. The next thing to think about is expiration and how to kind of encode that in our store. And what we can do is go ahead and to each of these fields, we're adding a new, or to each of these like union members, we're adding a new field called expiration, which is of type option datetime. And a datetime is a type in Effect that represents a datetime. It's a bit more ergonomic than the kind of default JavaScript date object and has a lot of like utilities and helpers. And so if the expiration is none, that represents a value that doesn't have an expiration set at all. And if the option is some, then the datetime represents when that value expires. And so to kind of abide by this, when we get from our store, we kind of wrap this in this larger function. And so the first thing we do is actually get the raw value from the hash map. But before we return it, we have to check if that expiration value is some. And if it's some, then we can compare it to the current datetime. And if the datetime is passed, then we return an option of none, which is the same as if the value wasn't there at all. You might notice that this doesn't actually delete expired keys. It just kind of like soft deletes them, like it wouldn't return them, but they would still stay around in memory. And to do this, we can kind of set up a cleanup job that will occasionally go over the store and take out expired keys. And we can set this up inside the layer that creates this service. So the key thing to like notice here is that we're first like creating an instance of this in-memory store at the top, and then we're returning it at the bottom. And that's really the main thing that's going on here. But then in the middle, we kind of set up this side effect where we call this purge expired function. And this is a function that goes over the store and checks all of the expirations to see if they exist and see if that key has expired, and then removes it if it's expired. And then we can, this layer takes in a duration, and then we can repeat this effect according to a space schedule on that duration. So if the input was like duration.minutes5, then we would repeat this purge expired function, the cleanup function, every 5 minutes. And then we're calling fork scoped, which runs this like repeated cleanup task in a separate concurrent fiber. And fork scoped ties that fiber's lifetime to a scope, and then using layer.scoped, that kind of absorbs that scope into the layer. So this concurrent task's lifetime is tied to the lifetime of the layer. The next thing I wanted to point out was I talked about the datetime module having a lot of different utilities. One of the ones I found particularly useful was this datetime.addDuration. So this came up in like this set like handler. And so set as a command takes like a key and a value and optionally has an expiration. And so if the expiration is some, we can get the current time and then use datetime.addDuration, which returns a new datetime, which is the duration past the first datetime, to get the actual value that we store in the database. And the reason I thought this was a really good example is because it really shows how the Effect modules build on one another. This API can only really exist because Effect has a very robust datetime module, and it also has a very robust duration module. And so it can write these kind of like cross-module helpers, where if you were using like a separate datetime package and a separate duration package, you would have to write these yourself. And this can kind of compounds to all the different modules in Effect. Now, if you remember our stored value kind of tagged enum type from earlier, there we were first declaring the type. But what we can do instead is declare that type as like a schema first and then derive the type from it. So we can make a schema for all the different, like the string and the list and the hash. And then we can make a schema for the entire store using schema.hashmap. And the benefit of this is that we can create these like transformation schemas that are able to transform from our store type to any arbitrary type. So a good example of this is if we want to make a snapshot. So Redis has like a special binary snapshot format. And so we can create a schema that is able to, that knows how to encode and decode from our in-memory store type to this like raw binary snapshot format. So speaking of snapshots, I implemented, there's two kinds of persistence in Redis. So there's file system, or there are both file systems, but there's log-based persistence, which appends, it's like an append-only file, and it kind of writes out all the, it's like the write-ahead log. And then there's like snapshot-based persistence, which is it kind of like stores a whole copy of the database every so often and on shutdown. And so I implemented both. We're just gonna look at the snapshot-based ones. And so the first thing we need to do is update our storage interface from earlier. So this was the one that just had that one run command. And so now because the storage interface is kind of opaque, we don't really know how it's actually stored. The storage interface has to tell us, like it has to be able to give us a snapshot. And so if you wanted, you could use like the schema technique I just described on the last slide, but really it could be anything. And so then I made a new service which represents a way to store a snapshot. So this just takes in the byte array and then does something with it. And one example of that is this like file system version, which uses the file system module from Effect platform to just write out that snapshot to this like file. And so now that we have these two parts, we have like a storage that can generate a snapshot, and we have a persistence service which can store the snapshot. Then we can combine those, and I'm doing this inside a layer. Namely, this is a layer that's like it says scoped discard, so the like discard constructors for layers. They don't actually produce any services. They just kind of have side effects. And so this layer uses both the storage service and the persistence service, and has this take and store snapshot variable. And you can see first it calls storage.generateSnapshot, which generates a snapshot, and then it calls from the storage persistence service store snapshot. And so that is like one effect that represents taking the snapshot, storing the snapshot. And then what we can do is very similar to the kind of garbage collection technique from earlier, is we can repeat that according to a schedule and fork it into a scope, and then using layer scoped. And so we can have this kind of asynchronous task that will take and store these snapshots every so often. And the other thing is that we're using effect.addFinalizer to make sure that like if the process gets interrupted, we take a snapshot right before we exit. The next thing I really wanted to look at was transactions. And for transactions, we're going to be using Effect's software transactional memory, or STM library. And this is kind of a niche part of Effect, but it will make implementing transactions, which is usually quite difficult, literally a couple lines of code. So before, or up until now, we've had a normal hash map. And all of our operations on this hash map are synchronous. We're just getting and setting to the hash map. But in order to use STM, we need to put this hash map inside a TREF, or a transactional reference. And a TREF requires that the type inside is immutable, but we kind of already have fulfilled that requirement because we're using Effect's immutable data types. And so before, where operations were just synchronous, or we could kind of wrap them in the effect type, now all of our operations on the TREF become an instance of this STM type. And you can kind of think of STM as like the sibling to the effect type. It has the same 3 type parameters of like success, error, and requirements. But where an effect represents a like possibly asynchronous, possibly effectful computation, STM represents a pure transactional computation. So they're kind of like slightly different things, but with very similar APIs. And so what we do is, next slide, there we go. We can kind of call the related, so I have like this function which returns an STM, and you could like do one of these for each of the operations, like get or set, but here I just have get. And then we can match on the command that comes in and call the related function. And so we get back an STM, which represents like the update to the TREF, but we haven't actually committed it yet. It just kind of, it's like an effect that you haven't yielded yet. And so then we can use stm.commit, and that returns an effect that represents actually running and committing that transaction. And so this isn't really that different from what we were doing before with just one command. But for example, if we wanted to bring in an array of commands instead of just one command, for example, in a transaction, what we can do is map over this array with that same get command STM function, and we'll end up with an array of STMs. And then just how we use effect.all to turn an array of effects into an effect of an array, we can do the exact same with STM. And so now we have a single STM, which represents all of the kind of individual updates for each of the commands. And then because we just have one STM, we can just commit that one STM. And because STM operates as like it either like commits or rolls back, that's transactions. That's all you need to do. And Redis doesn't actually have the concept of rollbacks too much. I think it might be possible in like the Lua code, but just with like normal commands, it doesn't really have that concept. But if we wanted to implement that here, it would also be possible. You can just fail from an STM, like just how you like effect.fail, you can stm.fail. And if like we have 5 commands in that array, and the first 3 succeed, but the 4th one were to fail, then the whole transaction kind of aborts and the TREF never gets updated. Here, so I made this other service that's called the transaction driver, and this is kind of represents like the external way of interacting with transactions. Really, it's just a wrapper around this kind of like internal state, which is an option of an array. And so if the option is none, then there's no transaction in progress. If the option is some, then the array represents the queued commands. And then the service just kind of abstracts on that a little bit. It has like a effect to if a transaction is in progress, and it's like starting one, appending a command, aborting a transaction, and executing it. The next thing is pub/sub, and Effect actually has a type called pub/sub, which basically did 90% of what was needed. And so very similar to the transaction driver, this has its own service, which just has a slightly abstracted interface around a kind of like inner pub/sub instance. And it returns a stream, which you can like subscribe to, and then that stream gets converted into REST and then kind of forwarded through that like pipeline shown earlier. And then Redis, it's like a server. You usually need to start it over CLI, and we're using Effect CLI for that. I didn't get too deep into this part as it's pretty simple, but I just wanted to point out this like option, this like port option as a very good example of the declarative API that Effect CLI gives you. So this represents like options.integer. So this represents like an option. So like it would say like -- port equals 3000. And then we can give it these like additional combinators. So we can give it an alias, so it could work with like just -p. And we can give it a default value, and we can also have it fall back to an environment variable. And then we pass this into command.make. And then command.make gives it back to us in the arguments for the handler, so that like in that final handler inside the object, the port is just a number. And it's kind of like, did it come from the environment variable? Did it come from the default? Did it come from being passed to the CLI? It doesn't really matter. We just get it back. And then we can provide that to the layer constructor for our socket server. And that is what actually changes the port that the socket server starts on. So I know that was kind of a lot, actually a lot of code, a bit more than I wanted. But let's try to take a step back and really like distill down Effect's key impact points. I think the number one thing here is just working on top of fundamentally better primitives. I think the effects of using Effect over promise have really been talked about a lot. I think people are very familiar with that. But in the same way, the stream types in Effect really shine over their Node and web counterparts. And so it's not just the effect type, it extends to streams and channels and STM, and really these things are possible because they're built on really robust primitives. And so all the things we love in Effect, type safety, error handling, dependency injection, interruption, declarative APIs, all kind of stems from these primitives. Next is swappable services and dependency injection. And this is used a lot in this app. We have like the transaction driver, the pub/sub driver, the storage interface, the persistence, both like the snapshot persistence and the log persistence. It's all services. And this is really great for testing and composability and swapping out implementations. And then finally is the rich effect standard library. And this is just all over this app. So we're using schema for the encoding and decoding the RESP, STM for transactions, pub/sub for Redis pub/sub, date time for doing the expirations. There's option, duration, schedule. I didn't get to talk about it, but I used match as well for pattern matching. And then from Effect platform, socket and socket server, and file system. And then finally Effect CLI. And yes, OK, moving on to performance. I want to investigate performance a little bit with this app, considering this app's kind of relative complexity, and also that Redis ships with a binary called Redis benchmark. And considering that Effectis is Redis compatible, I was really curious to see how it would hold up. The answer is not well. So on the left is the official Redis implementation, and on the right is Effectis. Now, I know this looks pretty bad, but to be fair, Redis is written in C, and it's been highly optimized for a decade. And I spent a total of 0 minutes trying to optimize Effectis. I really tried to like give Effectis like a much more fairer comparison, and that would be like a Node JavaScript implementation of Redis that's not using Effect. But I really couldn't find one. And I could have implemented it myself, but I think implementing Redis once was enough. And also, the whole idea was that using effects is like the fun, like easy way to do this. So I didn't really want to do the annoying hard way. So from now on, I'm just going to be comparing Effectis to itself. And so the first thing I did was we used Bun, and Bun gave like a 30% jump, which was pretty good. You might be curious about the V1 at the bottom there. And it turned out my original version, the zero optimization version, kind of sucked. what I was doing was, while my schema-based parser was very, very cool, it was not the most efficient because it wasn't an incremental parser. So it only, like, you could give it a string and it would either succeed or fail. So what I did was I took the input string, split it into individual characters, and then we just append on one character and like run the parser, and it would either succeed or fail. And then I'd append on the next one, append on the next one, and you can kind of imagine that there would be a lot of failures before one success. And so it turned out that 30% of my code execution time was just constructing error objects. And so I found a library on NPM called Redis parser. I don't actually think this one is particularly efficient as well, but it's a little bit better. And especially the way I wrapped it. I like turned it into a node duplex stream, and then you can turn that node duplex stream into an effect channel. But with just that, we were able to double the performance, so that's pretty good. And this was also kind of expanded to Bun as well. Now again, I don't have a like non-effect version to compare to, but like if you imagine, or some people are often concerned about effects performance. Here's why I don't personally think it matters too much. Really the comparison is not against native languages, but against non-effect.js, which I think the effect slowdown is definitely not on like I think the original versus the Redis implementation was like 300 times slower, or it was 300 times faster. And so when you're looking at like effect versus non-effect, you're looking at like probably 2 to 10 times at the most. And so, okay, even less, 20% says Mike. So. But still, there is always going to be some costs. There's a runtime, you're wrapping your code in all these objects, there's a lot going on. But really, the main use for JavaScript on the server is not highly parallelized CPU-bound code, it's business logic. And in business logic, async rules supreme. And this is because async costs, like network calls, they're shared equally by all code, whether slow or fast, and then they're usually kind of orders of magnitude larger than even large sync discrepancies. So I created this chart, and you can kind of think of these like two implementations of a server. And this represents like client response time. So I like make a response to the server, how long before it comes back. So we have two implementations. The green one is 10 times faster than the blue one. And so on localhost, where there's no network delay, there's a pretty big gap. But as soon as you're looking at like 30 milliseconds, this is like a nearby city, you're already down to just 29%. And if you're going across the globe to another continent, you have 100 milliseconds plus, which is down to less than 10%. And this stuff is unavoidable, it's just speed of light. Now you might say that while the client times might not be that different, still like my server can handle, the green one can handle 10 times the throughput. And this is true, but this is less of a concern in serverless apps, which are a very, very popular way of running JavaScript on the server these days. The other thing that's really important to mention is that Effect puts you on the path to writing more performant async code by default. And this can actually make up for the kind of smaller sync performance losses you might see. And this comes from stuff like structured concurrency and proper interruption, where in promise land, you might spawn just like way too many promises, or you can drop a lot of promises, which would still eat up execution time, even though they'll never be consumed. And I also talked a lot about primitives so far, and using Effect means working with like the right primitives and the right abstraction from the start. And it means you're not hacking together your own worse, slower version of Effect, which would obviously be less performant. And it also means that the really talented developers on the Effect team can do these like low-level runtime optimizations for you and ship you that over updates. And so I've been told that Effect 4.0 will have some small performance improvements to look forward to, that all of the users, obviously you didn't have to spend any time on that. Now, you might notice I left out clustering, kind of like the big elephant in the room, all the way at the top of that complexity chart. And clustering is really hard to get right. But obviously earlier we saw Effect Cluster. And Effect Cluster is really, really exciting. Unfortunately, while I was working on this, I just wasn't ready yet. It was kind of in pre-alpha, which is not particularly when you want to be using a library. But once it's more stable, which now I think alpha is like stable enough, I'd really love to try to get like a Redis cluster style API using Effect Cluster with this project. So finally, a quick recap for what we covered today. We looked at Redis, which is a real-world app with kind of advanced higher-level requirements. So there's like expiration, async, networking, transactions, persistence. And we looked at how Effect's tools in practice really give us a strong foundation to build apps that have to take on these sorts of challenges. We looked at a brief performance analysis and ultimately why I don't think Effect's very small performance penalty matters too much for async limited business code. And finally, some future stuff to look forward to with Cluster. So if you're curious, all the sources available on my GitHub. There's a lot of stuff that I didn't get to talk about that might be worth looking at. And of course, you can find me at Ethan Niser on everything. It was really a pleasure to be here to talk to you all today. Thank you so much.